Good afternoon and welcome to the Sustainable Materials Management webinar series, a joint effort between the National Recycling Coalition and the Pennsylvania Recycling Market Center. My name is Wayne Bowen and I'm the program manager for the center and will serve as your moderator today. We would like to extend a special thanks to Bob Hollis of the Mobius Network for providing the webinar management software for this series, and Lisa Ruggiero and Laura Flagg of the National Recycling Coalition for assisting the RMC with that webinar promotion and technical support. Today's webinar focus is on organics management and sustainable renewable energy. Our presenter today is Keith Henn, who I'll introduce in a moment. Following this presentation, we will conduct a question and answer session. If you have a question or comment, please use the GoToWebinar dialog box located in the control panel on your screen. You may also use the dialog box to request assistance if you're experiencing technical difficulties during the webinar. Please note that an edited version of this webinar will be made available for viewing via YouTube links on the National Recycling Coalition and Pennsylvania Recycling Market Center websites. And now I'd like to introduce our presenter. Keith Henn is Vice President of Bioenergy at Tetra Tech, Inc., and has more than 20 years of experience in energy management. In his current capacity, Mr. Henn manages biogas, waste-to-energy, bioenergy, biomass energy management, climate change, and greenhouse gas management business lines. He has worked on various waste-to-energy and bioenergy feasibility studies and designs for food waste and anaerobic digestion systems on projects with a value up to $50 million and programs up to $500 million. And okay, so Keith, you're on, and you can take over the presentation.
Great. Thank you very much, Wayne, and welcome everybody to the seminar. I'm very happy to give this presentation today after we've seen an evolution in the solid waste industry and specifically how organics are managed. Just briefly about Tetra Tech. Tetra Tech is the firm that I work for and have been with for just about 20 years. We're a large firm with global presence, and we're ranked by Engineers News Record in several of these classifications. I put this slide up here because we have a lot of experience in solid waste, of which we'll be talking about today. And I think the paradigm shift has not only occurred in our company over the last decade, but certainly as an industry in general. So we'll move on to the next slide. And the next slide, carrying over from that solid waste, talking with several colleagues within the company, I think when you talk with solid waste individuals or people that have experience with municipal solid waste, and these traditionally are landfills and the management, the hauling, the design, the build, the operation of these landfills, this is a very huge industry in the United States and of course across the world. But one of these individuals with at least 25 years of experience sent a note out to a number of folks and said, hey, take a look at this. This is an announcement back in September of 2014 that Governor Jerry Brown from California signed 2 landmark pieces of legislation. This was identified in BioCycle. This isn't news to BioCycle, but perhaps it was news to a number of individuals that hadn't seen this or really hadn't paid much attention to this paradigm shift that I will talk about today. The next slide illustrates the traditional waste paradigm, or the waste pyramid, if you will, and the bottom of that pyramid is the predominant amount of work and where waste goes to in the United States and North America in general. And traditionally, most of that goes to landfill. Some of it has gone to transformation or conversion technologies, including waste to energy. There has been certainly a great deal of recycling and compost, as well as reduce and reutilize the material. But the next slide, and this is a bit of an animation, hopefully it'll come across, this has been flipped on its head, if you will, in terms of the industry. And the industry has changed and transformed in this paradigm shift over the last several years, and it could be varying degrees, a number of years, depending on who you speak to. But the focus now has been to reduce the amount of material that goes into the landfill, still utilize as much as you can for that transformation, the waste to energy segment, but also convert it into compost and other usable materials. Certainly, we've seen a huge shift since the 70s on recycling, and most importantly, now we're focused on waste prevention and reduction of that. So these growth areas on the right-hand side require kind of a new thinking, if you will. It's no longer focused, or I should say the emphasis is shifting from a traditional landfill mentality of how we can receive, haul, receive in the landfill, store, and close these landfills. But now it's talking about things like zero waste planning and how that can be incorporated into this to minimize the materials that would go to the landfill. The following slide is a traditional diagram provided by EPA, if you will, that shows a general distribution of materials from an MSW. And you can see, of course, the bottom right is the recyclable type materials, glass, metals, and plastics that have pretty well-established programs throughout North America, no doubt. But there's a less so, and this is where the paradigm shift comes into play in the top half of the circle, or the pie, if you will, in that yard trimmings and food residuals and paper and the varying subsets of these is what referred to as the organic portion of the MSW. This has been a transformation, if you will. This is a large change in terms of how we manage that material. These organics, of course, one of the primary alternatives here is, of course, utilizing food residuals, pre-consumer residuals to feed people, and post-residual food waste to feed animals, of course. There's nothing new there. But there's, of course, a number of things in terms of industrial uses, utilizing for generating byproducts and primary products. But there's also composting that's been involved in the United States for decades. But anaerobic digestion is relatively new to the market, if you will, new to the U.S. market. And I'll talk a little bit about that in the subsequent slides. So this waste material is kind of being transformed in terms of utilizing it as a waste, but as, of course, oftentimes utilizing it as an organic material that can be alternatively used. Now, what are the drivers behind this process? This next slide that's up on the screen now kind of shows that there's a number of things that have occurred. I'd say probably originally in California, these assembly bills are ABs, AB 32, 341, 1826, and 1594, just to name a few from California. Those have probably started the process. I would say AB 32, the California Global Warming Solutions Act in 2008, talked about the reduction of landfill emissions. And in California, while certainly a very large economic and socio-political driver, sometimes for the entire country, a lot of times these regulations certainly start in that part of the country. And so for that, not only in the United States, but sometimes it evolves into other parts of North America, certainly our friends in Canada. So the numerous regulations that have started in the late 2000s, and then more recently in March 2014, the White House came up with a climate action plan to reduce create a strategy to reduce methane emissions, which would include a number of entities, including landfills. And then in Vermont, in Act 148, the Universal Recycling and Composting Act was taken care of. And Connecticut in 2013, the Public Act 13285, all of which focused on diversion of organics away from landfills and to utilize that in an alternative waste. The photograph on the bottom right shows a digester that would be located, if you will, at a wastewater treatment plant, and I'll talk a little bit about these different types and where these digesters can be located. So on to the next slide. Let's talk a little bit more about these regulatory drivers. And oftentimes, regulatory drivers is the impetus for these things, but it's also socio-political as well. And I'll say that in 2008, it originated, I would say, this recent renaissance in San Francisco, where they enacted a mandatory recycling and composting. And these three bins, the green, the blue, and the black bins, of course, are commonplace in that many parts of the country. But then in 2012, I mentioned Vermont diverting a plan in place to divert organics through 2020. And then more recently in 2013, the state of Connecticut passed a law that would be implemented in 2014 that generators with large amounts of material within a certain distance from a facility either must compost or AD or convert these organics through anaerobic digestion, or AD, to generate energy. And New York City put in a commercial organics law for large food generators, and that's gone through another cycle. Just recently, the mayor just announced on the 2nd of July of this year a renaissance, if you will, on some of those laws and to further enhance them, if you will, into the marketplace. And then, of course, continuing into Massachusetts, the disposal ban for those generators greater than a ton per week. And in Rhode Island, and of course, as I mentioned, AB 1826 and that being another example of many regulations that have put in California for commercial organics diversion. And AB 1594, that through 2020, the organic materials that are currently used as daily covers in landfills can no longer be utilized as daily cover. So this green waste material, and this would be yard trimmings and other things in addition to food waste, but these types of things, specifically the yard trimmings, have to be utilized for some other purpose other than for a alternative daily cover. So Maryland, and as well as other cities in the central and populous parts of the country, are looking at ways to divert these organics from the traditional disposal into the landfill and to utilize them for other purposes. Now, the next slide illustrates a graphic that's quite simple in that the population densities are certainly on the ends, if you will, the bookends of the country. And you can see that many of the states that I just mentioned, certainly California and New York and Vermont and Maryland and other states, have been generally focused on some of these newer laws in place, of which I've just scratched the surface on a number of them. And I think you'll see that the population density is certainly a factor here, but it's not the only factor. There's a number of things such as good stewardship and other benefits to handling this waste in an alternative means. And I think in the central part of the country, there's less regulation per se in a lot of these areas, but you're seeing a lot of corporate sustainability plans being implemented. And you're seeing some of those plans, including Fortune 100 and Fortune 500 companies, that are looking at how they can handle this waste differently. So this would not be driven by regulatory, as I've described in the last several slides, but it's also driven by corporate sustainability programs. For example, large corporations like Walmart and Target that have a number of waste byproducts through their stores and their operations, they're handling this material in a different way. Large food and beverage manufacturers are looking at, instead of disposing this to a landfill or taking it to a wastewater treatment plant for discharge, they're looking at managing this material in a different way. Shearer's Foods, for example, in central Ohio, who relatively has no regulations but has some incentives in the state of Ohio, they are looking at taking their potato chip manufacturing waste, and they have first phase already implemented a digester and utilizing that material to generate energy, as well as looking at a second phase going forward. So I've just given you a number of examples that are driven both by population density, the desire to manage this waste alternatively, both regulatory as well as from other drivers. So let's talk a little bit about those drivers on the next slide. And certainly the regulations that I've mentioned are driven by the diversion of organics from landfills. It's also, some of these regulations are also focused on avoidance of treating these materials in incineration. For example, in Connecticut, they're looking to, through their regulations, move their organic materials from the existing systems, landfills and otherwise, including incineration, but there are a number of those facilities in operation, and taking those materials to a compost or a anaerobic digestion facility. And then, of course, there's air quality, and of course the emissions as being a primary factor here. Of course, the organics material that's deposited in the landfill breaks down organically, and that emits methane as it's destroyed anaerobically. That methane emits to the atmosphere, so GHG, or greenhouse gas, as well as air quality, carbon dioxide, and a number of other factors come into play with the drivers behind the organics diversion opportunities. And then, of course, there's a number of major waste recycling firms that are already looking at these alternatives. I mentioned many food producers as well as retailers, but there's a number of waste manufacturing firms that are currently looking, I should say, recycling and hauling firms as well as landfill firms that are looking at alternatives. And these, some of them are driven by regulations and others are on corporate initiatives and sustainability plans. The added advantage of looking at alternative technologies such as anaerobic digestion as opposed to composting is that, of course, it generates byproducts. From composting, we're generally receiving a compost or a soil amendment or a soil product, but in the utilization of anaerobic digestion, I'll talk about in the subsequent slides, that you can generate energy in the form of biogas. That biogas can be transformed into electricity, into biomethane or thermal as well as fuels, and that adds added advantage because this material can be provided on a 24/7 or round-the-clock type of energy generation. So this provides a baseload power for our energy needs. So let's move on to the next slide. And the next slide describes a little bit about what bioenergy and waste energy is. I've mentioned to you about anaerobic digestion, but I think let's talk a little bit about the feedstocks or the material that would be utilized through the anaerobic digestion process. And in our view, in our Tetra Tech's view, we look at all things, that conversion of all things organic into an alternative byproduct into that bioenergy or waste energy sector, if you will. And this, of course, includes both the biological and thermochemical conversion of these materials, biological predominantly being anaerobic digestion and thermochemical being things such as gasification or pyrolysis. And those feedstocks, of course, municipal solid waste and certainly focused on the organic fraction of that. The food residuals that would be either pre-consumer, that is byproducts from a manufacturing process, or in some cases post-consumer, that would be source-separated materials at the user's location, and that material will be distributed and utilized differently, or it can be received from a transfer station or a material recycling facility or a MRF. It can also be agricultural residues such as livestock manures, or it can be byproducts from the growing and cropping industry. It can also be wastewater from human waste, and of course, as I mentioned, landfill gas. That material that is decomposed in the landfill can be then converted to energy otherwise. And of course, woody materials, as you're seeing here on a biomass plant in the state of Vermont. So let's move on to the next slide. And let's talk a little bit about this evolution, if you will. And of course, I mentioned sometime before, earlier in my slide, that incineration in the United States perspective has been predominantly the source of waste energy. But as you'll notice from this slide, particularly the geographic locations, as I mentioned, they're very similar to the higher populous states, but also notice the time frame from which these plants have been installed and operating. Frankly, to my information that we have here, as cited from the Energy Recovery Council, that there were 83 plants in operation as of 1994, but there was only one plant, one in the state of Florida, that has been installed, frankly, in the last 3 years or 5 years since 1994. So there's been relatively no drivers behind and no additional plants that are focused on the incineration, if you will, technology suite. So this thought and concept of bioenergy and waste energy has evolved from straight incineration to other alternatives, and I'm going to talk about the alternatives here in terms of anaerobic digestion, as well as I'll briefly mention a little bit more about thermochemical conversions. So let's go into slide 11, this slide talks about what is biogas. Essentially, biogas is gas produced through the breakdown of organic material in the absence of oxygen. So anaerobic, meaning the absence of oxygen, the decomposition of that organic material, which are generally materials that can be broken down in that environment. These generally do not include cellulosic materials or woody type materials. These would be materials that can be broken down in the backyard of your garden, if you will, in a compost setting. The same type materials would be utilized in this setting. The components of that breakdown would be generation of roughly between 50 and 70% methane. The balance of that being carbon dioxide, a small percentage of hydrogen sulfide, and water. This calorific value of being roughly about 50 to 70%, or 500 to 700 BTUs per square foot. But in this circumstance, this is the raw biogas. And a lot of times, as we'll talk about, that biogas is cleaned or purified, and that material can be further concentrated so that you have a higher BTU content of that material. The next slide shows a graphic that was put together by a combination of a number of entities, including the USDA, the EPA, and the American Biogas Council. And this graphic, including a number of entities across the board, both laymen and technical folks within the industry, graphically show the process, if you will, from a bioenergy and anaerobic digestion plant, optimizing the utilization of that organic material from the left-hand side of the screen, where that organic material is delivered, and that might be manures and or agriculture materials. It may also be food waste, both post and pre-consumer, pre and post-consumer waste, That material is transformed in an anaerobic digester. This can be a continuous stir tank reactor or a tank reactor or a complete mix system. It can also be in a lagoon setting, as well as other technologies such as plug flow. Those all, generally speaking, are what we refer to as wet digestion, but there's also the ability to transform this via dry digestion, and I'll illustrate a couple examples of that moving forward. This biogas can then be converted over to water, carbon dioxide, and the methane, as I mentioned, but the solids and liquids can be then transformed, if you will, to fertilizing material, fertilizers. It can be utilized in a number of other byproducts and conversion of those byproducts. The raw biogas can then be converted into electricity, thermal, and of course compressed natural gas, renewable natural gas vehicle fuel. On the next slide, kind of shows a couple of photographs of typical digesters, if you will, in the United States. And the one on the top is a traditional wastewater treatment plant where the human waste would be converted through anaerobic digestion as well as a number of other processes. And on the bottom left is the digester at Michigan State University. And those fine folks up there involve the conversion of both agricultural wastes in terms of livestock manure as well as food residuals from the university itself. And then on the bottom right is in the Rosendale Dairy from the University of Wisconsin Foundation. This is a anaerobic digester utilizing a complete mix system in the state of Wisconsin. So let's move on to the next slide. And here we'll talk a little bit about the market challenges. I think the competitors in the world, if you will, in the energy sector are quite numerous. Of course, the fossil fuels is a strong competitor to the bioenergy market space, but frankly, the anaerobic digestion, or specifically the bioenergy market, may have different ways to address this challenge. And the challenge being relatively low natural gas prices and the shale gases being abundant and frankly a glut of that material. But frankly, as I pointed out, the anaerobic digestion and bioenergy sector is not simply about energy. It's about waste diversion. It's also about managing the waste in a more meaningful and sustainable manner. What I mean by that is it's not always about generating the power that makes a bioenergy project successful, but it's also about taking that material that would otherwise go into a landfill and sustainably converting it into renewable energy as well as compost. Of course, there's other incentives such as what we call green gas incentives with the low carbon fuel standard, or LCFS, or the renewable fuel standard, the RIN credits that are a result of that, and utilizing the biogas for renewable energy credits, in this case for renewable fuel credits, and they can have additional incentives that would not otherwise be available to the shale gas industry. The other competitor of the challenge would be, of course, the relatively strong wind and solar market. But the challenges with both of these renewables, even though our firm does a number of things in that sector, is the fact that both of these are generally not considered baseload power. They're diurnal or spot power, if you will, depending on their location, and the relative ineffectiveness in all parts of the U.S. and low efficiency in certain parts of North America can be a challenge in certain circumstances. So in this circumstance, anaerobic digestion, waste energy, continuous feedstock coming in can provide a continuous baseload of power. Certainly, the complexity of these systems is much more, oftentimes require more sophistication and planning than do wind and solar, but there's a lot of experience in the sector. Our firm, as well as a number of other firms, have done tens and hundreds of these projects throughout the world and can bring that experience and have that experience in the United States. The capital markets can be gun shy, of course, about this because it's relatively new, if you will, to the United States, but certainly has quite a bit of potential, and I'll talk a little bit about that potential in a little bit. So I think lastly is this, we've always done it this way. We've taken our materials, we've done some recycling to be sustainable, but we've put this waste in landfills. But I think, as I've pointed out with the regulatory drivers here, there's a paradigm and shift in place that we can do things differently going forward. So let's move on to a couple examples. And as I mentioned, in California, the regulations that have been in place and have started in the late 2000s and and have continued to develop through 2008 into present has really provided a hotbed, if you will, for the potential in California. This location is the Zero Waste Energy Development Corporation and Zero Waste Energy Technology that's focused on a German technology, the compost gas technology. And in this circumstance, this is a 90,000 tons per year processing facility that is located in San Jose, California. So the materials are received on the back left. They are processed. There's a small MRF, if you will, inside the building on the left. And in the center portion of this facility, they have what's considered a high solids anaerobic digestion facility, where the material is taken in and put it into concrete modules or garage doors to make it simplify. The doors are closed. The material is transformed, if you will, into an anaerobic state where the material is further decomposed. The material is taken out of those modules or garage doors in the simplest sense, and are taken off-site beyond the screen here to do further composting. The graphic, if you will, on the right-hand side illustrates the biofilters, that material that has relatively high amount of odor from that material coming from the digester is managed through the biofilter to mitigate those odor challenges. Just quickly and incidentally, the two pillow top material, if you will, in the center portion of the screen is where the biogas is collected and stored, and then in the back portion of the photograph there is where the combined heat and power, or genset, is located, where that material was transformed from biogas into electricity. Let's move on to another example in Sacramento, the South Area Transfer Station. This is a project that was put together by Clean World as the developer and owner of the technology. And in this circumstance, this photograph is showing the 300 SAFM digester gas, but in this case, which is roughly about 300 tons per day, but it's actually being doubled as we speak, and it's to be going online, excuse me, not 300 tons, but I think it was 30 tons per day, and it's now being converted over to 300 tons per day. So in this circumstance, that biogas was transformed and is currently being transformed and cleaned up through a technology called BioCNG, where that material is being transformed and upgraded into compressed natural gas vehicle fuel, or RNG, and you can see the Atlas disposal truck on the bottom right, which is being fueled right at the facility. So the material at the transfer station, the trucks can dispose or drop in the transfer facility and then be refueled with compressed or renewable natural gas at the same facility. So let me go on to the next example on slide 19. This is a project I've hit on two in California. Now I'm going to hit on one in the state of Connecticut, which is being developed by a company called Turning Earth LLC. And Turning Earth is focused on similar high solids anaerobic digestion technology. In this circumstance, it's a little bit different than the one that was illustrated previously at the San Jose facility. The size of this facility is comparable, if you will, in that they're planning to process around 75,000 tons per year of diverted landfill organics, as well as yard waste at this facility. And the byproducts here, of course, are combined heat and power in the form of electrical power generation, as well as thermal energy that will be utilized on site, as well as adjacent to them with that bypass or that surplus heat being used for greenhouses, as well as the generation of compost. And I'm going to show you a couple photographs here. This is another illustration of bringing European technology to the United States on the next slide. And these photographs were taken by myself and my colleagues in Denmark. And this is a technology that has been operating for over 10 years in Denmark. And you can see in these photographs the module doors that are open. And again, I referred to these earlier as garage doors, if you will, because that's the simplest and most similar comparison. And the material is loaded into those garage doors or modules. And it's homogenized and loaded. And the doors are closed that you can see on the right-hand side. And material is water and other types of liquids are brought through the material. And that is a closed-loop system where that water is taken over and transported to the actual digester itself, which is shown on the bottom right. And that material is further decomposed through the anaerobic process, including the multi-steps of hydrolysis and fermentation steps. And from that point, biogas is generated from that tank as well as within the modules. And in this circumstance, this technology has some added advantage where the module doors remain closed after the anaerobic process, and that material is then converted from anaerobic to aerobic processes. And then, as a result of that, the composting process begins inside the same module. So the material is only moved once in this circumstance, where it's loaded into the module. It goes through an anaerobic process and then through an anaerobic process, anaerobic, then followed by an aerobic process. Then the material is taken out and further composted, as referred to as a maturization process. So let's move on to the next slide. Slide 21 illustrates for you the process steps for this facility in central Connecticut. And in the receiving building, this is certainly a mock-up of a rendering of the future facility, whereas step 1 is where the materials are received inside an enclosed building. Then those materials are transported over to the modules where the anaerobic and then subsequently the aerobic processes occur in each of the modules at various sequences in steps 2 and 3. Then that material is further conveyed over to stage 4, where that material goes through a maturization process and then stored temporarily for off-site sale in step 5. And the 2 tanks on either side of the modules, as I mentioned in the previous slide, are those tanks that continue the anaerobic digestion process, and the biogas is then generated and then converted via combined heat and power or an internal combustion engine. Moving on to the next slide, you can see an aerial photograph, a different angle. This is the facility with the closed roof now. And you can see a better view of the receiving building on the left, the central road, or the main street, if you will, between the modules that is now covered, and then the maturization bays on the right-hand side. And then what you also see in this graphic is a illustration of greenhouses that will be located both to the left side of the page and the bottom right side of the page, where those compost materials will be taking over and used as substrate for growing organic vegetables in this location, as well as the waste heat from the combined heat and power on the top center would be transferred over and utilized for the growing of those vegetables. Of course, from a seasonal standpoint, that waste heat won't be needed in 1 or 2 seasons out of the year, but in the winter months, we'll have full growing year inside of each of these greenhouses. So let's move on to slide 23. And wastewater treatment plants is something I mentioned earlier. Wastewater treatment plant is essential in every community as we're dealing with solid waste. In this case, the human solid waste that is pumped to the centralized facility. It's certainly also a value in the agricultural setting as well. So these are really important pieces of our infrastructure in each of our communities. But if you click down on the next slide, there is the problem with these wastewater treatment plants is they generally consume a lot of energy. And in some cases where anaerobic digestion is utilized in these wastewater treatment plants, biogas is often either, if it is generated, it's often underutilized or flared into the atmosphere. Now, if it's flared in the atmosphere, that is mitigating the greenhouse gas emissions. Of course, the methane being generated is flared, so it doesn't provide challenges in that regard. But this is a wasted resource, if you will, and it can be converted over to, as I mentioned in the previous examples, into combined heat and power or renewable natural gas. So the last click, if you would, is to illustrate the question: how can we transform this liability into an asset? These plants that are located in every community, were those plants that have anaerobic digestion, how can we convert that into a viable resource? And how do we optimize that biogas generated for beneficial resource? So essentially the challenge at bay here is that most wastewater treatment plants, as you might suspect, are utilizing just the human solids that are transformed and are transported to the facility via pumping and piping. But these facilities, as illustrated in many locations across the country, can be utilized to take these food residuals and other materials and transport them further, utilizing the existing infrastructure to generate more biogas, and that biogas can be beneficially reused locally, either in the wastewater treatment plant or surrounding community. So let's show an example on the next slide. This is in the city of Portland. This is a project we've done a number of years back. This is the Columbia Boulevard facility, which is one of the larger wastewater treatment plants. And you can see in this circumstance a Jenbacher engine that was operating, and they have an excess amount of biogas that they've generated as the plants have come online and there's been modifications, but that biogas is not currently being utilized. So the study that we went through, and I believe that this is almost in the implementation phases right now, was to look at what to do with that additional biogas. And that additional biogas could be utilized either in a genset, doubling the power from 700 kW to 1.4 megawatts or 1400 kW engine cogeneration, which is shown in the red, or it could all go to renewable compressed natural gas, or it could be used in a combination of both. And that would be illustrated in the green line. And as you can see, the interesting thing about this is that there's very good similarities between utilizing all that biogas in the genset, an additional genset, or taking some of that biogas and converting it into compressed natural gas vehicle fuel that could be utilized for the fleet. And to my understanding, as of about 3 months ago, that they were still in the process of going through those steps to evaluate and implement the compressed natural gas alternative. So let's talk a little bit about that on the next slide. This is an illustration that could be easily utilized in a compressed natural gas from a fossil fuel-based natural gas, but the added value that I mentioned earlier on in the process is that renewable compressed natural gas can be generated both at the source or very close to the source where it's utilized. The photograph in the top right shows a waste management vehicle that is being fueled at a landfill gas facility, whereas the landfill gas is cleaned, purified, and upgraded, and then can be transformed and utilized in the transfer trucks or trash trucks. But it can also be utilized as illustrated in the bottom right, to be municipal vehicles or buses and bus fleets. It's most economical in these captive or infrastructure, captive fleets or owned fleets and infrastructure. But as I challenge that this can be added advantage to others, such as those at wastewater treatment plants and other locations, as I pointed out in the last slide. I want to illustrate this further in the next slide. This is a project that BioCNG was involved in. BioCNG is a part of Tetra Tech, the Cornerstone group. The Cornerstone Environmental Group is part of Tetra Tech. And this is a project in the city of Janesville in Wisconsin where a wastewater treatment plant was generating biogas, and a slipstream of that biogas was utilized, cleaned, and you can see that microturbines were utilized for some of that biogas, whereas others, the gas was compressed after purification and upgrade, compressed and utilized in a natural gas vehicle fuel, and generating about roughly 100 gallons of gasoline equivalent of storage in that sphere, and utilizing it comparable to conventional fuel stations. So this provides a very unique opportunity here, both on the small scale, such as 50 cubic feet per minute, as well as up to 200 cubic feet per minute, or it can be utilized in series. But of course, it can go to a larger scale, as I pointed out in the previous slides. Let's move to a more of a regional slide here now. The audience here is focused on, with the RMC, focused on Pennsylvania, so I decided to throw this slide in as it's my home state. Pennsylvania is one of the top 5 states in the country that has anaerobic digesters in operation. There are approximately 30 digesters that are operating on Pennsylvania farms currently, and I don't know the exact number of farms that are utilizing organic substrates, or what we would call co-substrates or food residuals on the farm, but I think that number is roughly about 20 to 40% of those farms are utilizing outside substrate or food substrates outside of the farm in combination with the livestock manure. This photograph is from Yippee Farms in Mount Joy, Pennsylvania, where grease trap waste from local restaurants is being collected by a manufacturer and is being utilized inside the digester at this particular farm to increase the amount of biogas generated from the anaerobic digester on farm. I also want to point out that wastewater treatment plants, there's about 11 operating in the state, generating about 14.5 megawatts of power. And just recently, we're fortunate enough to be selected by Penn State University to implement a on-farm, on-campus wastewater treatment plant for, I should say, not a wastewater treatment plant, but an on-farm, on-campus anaerobic digestion facility to convert the livestock manure from multiple animal types on campus to be utilized at the facility. And I'm moving on to the next slide to illustrate quickly, although the focus of the presentation is not on thermochemical, but there's certainly a number of advanced technologies focused on gasification and pyrolysis and the utilization of those materials through those technologies to generate syngas, as well as in the conversion of that syngas to a number of other beneficial uses. Certainly liquid fuels and oils are certainly advantageous as the byproduct and the primary source, if you will, a primary product of thermochemical conversion. For certainly thermal heat, as well as combined heat and power, as with the previous examples, is certainly advantageous and can be generated from these conversion technologies. So let's talk a little bit about future drivers here in the last segment of the presentation. And the future drivers really come to form of many types, but I'm going to hit on two particular types. The Biogas Opportunities Roadmap that was generated by the U.S. Environmental EPA, the USDA, and in partnership, of course, with the Department of Energy in August 2014. Certainly, it's been documented and well demonstrated the biogas industry is well proven. There's over 8,000 digesters in Germany and Austria, 50,000 in Nepal, and millions of digesters on a much smaller scale in China. But there's relatively few biogas systems on farms in the U.S. But research suggests, as documented in this roadmap, that there are additional 8,000 livestock operations that are candidates to support biogas projects, in addition to the already existing 239 AD facilities on farms across the country. So if its full potential in the United States just on farm digesters alone, were to be realized, then the cost-effective biogas industry could produce enough energy from the livestock sector alone to produce power for over 1 million average American homes in size. So it's important to point out the magnitude of the opportunity here for utilization of anaerobic digesters, both for organics, and those organics being from municipal solid waste, as well as on-farm organics. So this strategy supports the Climate Action Plan, a strategy to reduce methane emissions in the country that has been defined and led by the White House. And so there's a great deal of potential here. I'm also going to point out another thing that, although in some environments might be controversial, but there's certainly an opportunity to utilize the Clean Power Plan that was recently released by the EPA, and to utilize anaerobic digestion as one of those many sources. I should say bioenergy in general, and waste energy in general, but certainly anaerobic digestion being one of those subsets to add renewable energy on a large scale. The Clean Power Plan focuses on solar and wind. There is some mention, and I believe in the coming weeks you'll see more discussion, if you will, as EPA comes out with additional clarification on what other types of renewables can be considered to support the Clean Power Plan. Of course, the state, as I mentioned, is a large driver that will have a huge impact on the implementation of the Clean Power Plan. And that was just discussed on the previous, on the next slide there. So you can advance the slide one more. So these are just illustrations that come off the EPA webpage on focus on the Clean Power Plan. And lastly, I'm going to share just briefly for you a couple of sources, several sources of information, the American Biogas Council and AgStar and so forth. And lastly, I'm going to finish with a little pop quiz. You can go about this at your leisure, but just briefly I'll talk about, there's a number of solar, geothermal, wind power projects, but how much of that comes from biomass and biofuels? And the next slide will illustrate that, frankly, a large percentage, maybe might surprise you, that 49% of the renewable fuels and energy come from biomass. So if we advance to the last slide, next slide, please. Here you can illustrate the slice of the pie, if you will, from renewable energy, and of that 9% from 2012, of that 9%, 49% is generated from biomass, whether it be biomass waste, biofuels, or wood-based biomass and waste energy projects. And lastly, on the next slide, I'll share with you a nice little cartoon that perhaps 5, maybe 10, 15 years from now, although landfills will probably never go away, but maybe our current and future generation will look at landfills perhaps in another light, if you will, as we transform and we continue with this paradigm shift in terms of how to manage organics in the current environment. With that, I thank you very much for your time.
All right, thank you, Keith. Great presentation. We're now going to field some questions for Keith. Again, if you have a question, please enter them on or in the GoToWebinar dialog box on your control panel. We do have a few questions already, so I will start with this one. When sending food scraps to anaerobic digestion, what technology is being used to economically clean up or process the loads from cafeterias or worse, curbside household collections?
Well, that's a good question. I don't have the question. I'm not able to read the whole question on my screen, but nonetheless, there's a number of different processes that can be utilized to transform these organic materials. And of course, the most efficient way is to do what was referred to as source separation. In this circumstance, at the source, the material is separated by the consumer or user, and I mentioned before the different bins. That is the most efficient way to extract those. Then the second alternative would be material recovery facility, and there'd be clean and dirty MRFs or MRF or MRFs. And in this circumstance, the materials can be separated from organics, from recyclables, from trash materials, and otherwise where those materials are split in different locations. There's a number of technologies that are out, both U.S. technologies as well as technologies from abroad, where those materials can be easily transformed through a MRF, or as well as other things such as transfer stations. And these can be implemented in a very efficient manner so that each subset of the materials can be taken off and taken in different locations. The photograph on the bottom left shows an example of one of those, a very small case or a small example of a MRF where the material is being sent over into a conveyor. That conveyor is going up to a material a recycling facility where some of the organics are separated. There's also, in this case, a DOTA separator, a manufacturer from Germany, where the materials such as plastics, and in this case metal cans and things, are separated and split. So those things that are non-organic that would go to recycling are not going into the digester in that case. So there's a number of technologies that are out there that can handle this.
Yeah, Keith, the bottom left photograph shows the bio-optic technology, which is basically humans looking at the material and sorting it out before it gets to the process facility.
That's right. And on the other side of that conveyor is where the DOTA separator is located. So oftentimes you need multiple types, if you will, to manage that.
Mm-hmm. Another question, after anaerobic digestion, are soil nutrients, and such as phosphorus in particular, are still available for use in the agricultural / fertilization, or are they permanently lost in the process?
That's an excellent question. And if you were to, that's one of the advantages, clear advantages of anaerobic digestion over the other technologies, and this is being strongly considered in certain places such as the Chesapeake Bay in terms of its implementation. The short answer is they're not lost. They're transformed or they're mineralized, whereas the material, phosphorus and nitrogen are transformed, and they're in a more pure state, so they can be removed more effectively. They're not lost. There's essentially a net zero, if you will, on those nutrients as it goes through the digestion process. But because they're mineralized, they can be utilized better. If you will, both ammonia and phosphate or phosphorus can be removed through subsequent processes after the digester. And the reason why I bring this up in terms of nutrient-strapped locations such as the Chesapeake Bay, as a number of states, including Pennsylvania and Maryland and Delaware and others, and other watersheds, if we're looking to minimize the discharge of those nutrients into these watersheds, anaerobic digestion can be very helpful. And in that regard, both on farm as well as in the wastewater treatment plant, the combination of an anaerobic digestion system with nutrient removal is a very good technology suite that can be utilized effectively. And so that's another illustration of in addition to the energy focus, in addition to the landfill diversion, in addition to the sustainability, in addition to the baseload power, nutrient and water quality management can be enhanced by utilization of anaerobic digestion. These are advantages over, say, traditional composting, whereas that's not able to be done in those circumstances, or can be, but just more complex steps.
Okay, Keith, I have a question on wastewater treatment plants. I know in a community near where I live, they flare the gas off of their digester, and I questioned them and asked them, can't you just put in a collection system and a gen set and make energy out of that flared gas? And he told me that the plant's too small to justify the capital expense of putting in that type of system. So I guess my question is, what are your thoughts on, is there a break point as far as size for these systems, or is there technology out there that can handle smaller generating facilities?
Well, the answer is to both is it depends. So generally speaking, there are rules of thumb, if you will, from wastewater treatment plants in terms of the number of millions of gallons that they can produce, if you will. That is of material that they transform to what they can generate. But there is economies of scale here, and certainly as plants are larger and they can handle tens of millions of gallons per day, if you will, of human waste, there increases the economies of scale and the potential for the return on investment. So I think it really is going to depend on a number of factors, but there are rules of thumb to kind of start those processes out. The other component here that is important is essentially that you mentioned about the technologies. Yes. So simplistically speaking, in almost all digesters, you of course have to maintain a temperature of roughly about 95 degrees Fahrenheit for a mesophilic system, and of course that temperature is not naturally achieved via ambient operations. So at a simplistic manner, most, if not all, digesters should probably be utilizing that biogas, even if it's a small amount, to fuel a boiler. That boiler can then transform into heat, and that heat can be utilized to warm the digester. So that increases the operational efficiency of the digester if it's utilized. So those sorts of things are certainly a minimal step. And as you go larger, then you can look at other things such as combined heat and power, look at things such as renewable natural gas, etc., like I talked about. And so this, of course, is some of the challenges with bioenergy, whether it be wastewater treatment plants or farm, is that they're not very simple. Every case may be a little bit different depending on the feedstock they receive and the retention time in the digester, et cetera, et cetera. So the answer is yes, and there's lots of options that should be considered.
Okay, this question has to do with the natural gas boom in this country, particularly in the Northeast. Has that impacted the price of methane from these facilities, and how does that affect the economics of AD projects?
Well, there's no question it does have an effect. And I'm not sure exactly what the Henry Hub price right now is for natural gas, but of course, it being in the $3 to $4 for MMBTU, these have really put a difficult environment for developers and implementers for these types of technologies. However, as I stressed in the presentation, this is not always an energy play. And so these types of projects, whether it be in a wastewater treatment plant, there is a potential revenue stream that can be generated from the tipping fees of the organics that would otherwise go to a landfill that would be received by the wastewater treatment plant or by the bioenergy project or anaerobic digestion project in and of itself. In other words, what I mean by that is essentially the relatively low energy costs right now can be offset by relatively high tipping fees that would be received by organics facility that would be located close to these feedstocks. So in that case, in some circumstances, the energy is really gravy or icing on the cake for a project, whereas the tipping fees are the primary revenue stream, particularly on urban environments that, particularly in the Northeast or in some places, certainly less so in California, whereas the tip fees that are carved out for organics are relatively high. So these materials would be received and it could be transformed. I also mentioned that, of course, bioenergy projects are not always energy driven. They might be driven on sustainability, They might be driven on regulation, as I pointed out in the early parts of the presentation. There might be benefits that are less tangible, but things such as renewable energy credits. It may also be nutrient removal and a host of other things that come into play. So the business model, unlike solar and wind, where it's entirely driven on energy pricing and the buyback price of the material, in this circumstance, it has many more components that can offset the relatively low energy cost. The other factor that's important to consider is the remote nature of some of these facilities. Natural gas may not be available in all these locations. In some of these farming communities, in some of these rural areas, whereas natural gas is not available, there's no pipeline, there's no infrastructure in place, so that has an independent effect. And this is particularly the case in biomass and the biothermal projects where there might not be natural gas. And Vermont is a perfect example of that, where natural gas grid may not be available to everybody. And so biomass materials and even anaerobic digestion can be independent, if you will, of that. But it's not to say that it's not a factor. It certainly is.
Okay, thanks. I think we're done with the questions. One last call for questions. Meanwhile, I'll close out the webinar. Again, this webinar, like all the webinars in this series, has been recorded and will be made available via YouTube links on both the National Recycling Coalition and the Recycling Market Center websites. And thanks again for joining us, and we hope you will join us for next month's webinar, and you can visit the NRC and RMC websites for the schedule updates. Thank you everybody for attending, and thank you, Keith, for taking the time out of your schedule to make this presentation. And so I'm going to log off here, and have a great day, everybody.